to noise ratio is very high.
Any other question? Okay, if there are no more questions, if there are any questions, somebody was asking. Hello, please go ahead. I don't see any question in chat box. Somebody was asking and stopped. Really. Anyway, if there are no more questions, let's thank Gautam once again. Thank you, Gautam.
Thank you very much. Thank
for
you.
giving your time and giving such a nice talk.
Thank you.
You there?
Yep, I'm here.
Very good.
Yeah, right.
So, third and last speaker of the session is Dr. Ashok Vudayagiri. It's a pleasure to introduce my old friend, Ashok. And sometimes people used to confuse between Ashok and myself when we were in Hyderabad. Okay. Long time back, when my hair was also slightly back. Now one can perfectly distinguish.
For some more years, yes.
Yeah, so Ashok has done PhD from University of Hyderabad itself. Then he went for a postdoc to US University, Rice University, with related postdoc on laser cooling and all. Then he was a visiting scientist in RRI, continued working on laser cooling and all. And he continues to work after joining as faculty in University of Hyderabad. He continues to work on laser cooling of atoms. Along with that, he works in quantum optics. His PhD was in quantum optics. And he's working on optical tweezers as well. So title is not announced for Ashok. So let's see what Ashok is going to talk about in this meeting on quantum information, quantum technology. So over to Ashok. Yeah.
Yeah, thank you very much, RP. Let's see if I can. I'm trying to share my screen and it's taking a little while. Just for a second. Yeah. Yeah, I hope it's visible. This is it's a mixture of slightly older work and what's going on with this right now. It's a theoretical work. It's going further from all my works built on in laser cooling. So just a second. Yeah. Okay. So I hope my screen is visible to everybody. Is the screen visible?
Yeah, it's visible. Yeah.
Right. Good. So the part of the things was done for younger audiences. So I'll go a little bit basics in the beginning. So we have spin quantum number. Every system has a spin quantum number, up or down. Basically, what it means by up or down is this, that if I take a collection of atoms, all the spins are randomly oriented and there's no specific orientation of it, the net spin will be 0. And if I put a magnetic field, all the spins will try to align depending on their quantum number. If it's plus or minus, they'll align either along the magnetic field or opposite to the magnetic field. And that also gives in a classical picture what we had called as Larmor precision. And therefore, the plus spin will have a h cross omega L by 2 energy. The minus spin will have a minus h cross omega L by 2 energy. And more than that, what is important is if I have two atoms with two different spins, it doesn't have to be atoms, any two entities, quantum entities with two different spins. When we bring them closer, there is a dipole-dipole interaction or a spin-spin interaction, depends on how you call it, because dipole-dipole is usually specifically reserved for a system which has one excited state and one ground state, and because the interaction will be dipole interaction, so therefore that will be a dipole-dipole. If I have two atoms what I'm going to talk more about as two atoms in ground state, both of them in ground state. So it's strictly not a dipole-dipole interaction. It's more of a spin-spin interaction. The configuration is more or less similar, except that the value of this gamma 1, gamma 2 will change the exact value of that. But nevertheless, the nature of interaction is very identical, whether I have a dipole-dipole or a spin-spin. In this particular example, I'm mostly concentrating on the spin-spin interactions. So I'll continue to call it as a spin-spin interaction. Okay. So again, because this was originally done for some of the early just out of MSc students. So we have S and P levels for any atom, which we know. And because of the spin orbit coupling, we'll get a division like the P becomes P half and P 3/2. But then for most alkali atoms, it also couples the nuclear spin and gets split into further divisions. And this is pretty much the scenario for all the alkali atoms on the first column, rubidium, potassium, sodium, etc. So what I'm talking about is works well with any of those atoms. And in particular, we are going to consider F equal to 1 and F equal to 1. And both of them are a triplet because they have Zeeman sublevels, 3 Zeeman sublevels, because F is equal to 1, going from -1, 0, and +1. And that's what we're going to concentrate on. Again, it can be rubidium, it can be sodium, any of these things. But as of now, the theory is worked out for 87 rubidium, but it can be used for any other atom which you can trap and have it. So we'll have the S half and the P half. The Zeeman sublevels are this. I've labeled them as G minus, G0, G plus, and the excited ones are E minus, E0, E plus. And they can be coupled in several different ways, depending on the polarization. The selection rules are dependent on the polarization. The ones which are pictured in red are the pi polarized, which are linearly polarized with their polarization in the Z axis. Z is also the axis of quantization, which is more or less determined by the applied magnetic field. And the sigma plus and sigma minus are respectively angular momentum adding and angular momentum subtracting. They loosely correspond to the RCP and LCP. Why I said loosely corresponding is normally in a optics book, RCP and LCP are defined with respect to the propagation direction of the beam. So with respect to propagation direction, if the helicity, the polarization vector is rotating clockwise, you call it RCP. If it is rotating counterclockwise, you call it LCP. But when it comes to atom light interaction, we slightly want to redefine it. So anything that adds an angular momentum will become sigma plus. So not strictly an RCP with respect to the beam direction, because it's more with respect to the magnetic field direction, the axis of quantization direction. And anything that reduces angular momentum will be sigma minus. Okay. The reason is a light coming from left side with an RCP could be angular momentum adding. The same beam coming from right side could be an angular momentum subtracting. So we want to be more specific on definitions, as sigma plus is one which adds angular momentum, sigma minus which subtracts an angular momentum. Okay, so now this is the configuration, and what happens is, suppose we switch off the sigma plus sigma minus and have only the pi polarized beams. Then the atoms, in the beginning, atoms are populated equally among all the 3 ground states. So or we can have this configuration also. Let's first see what happens if we have only this configuration, only pi polarization presence. Then the atoms get pumped up, and then they can come down either to the same level because of spontaneous decay, or they can go back over here. But if they go to the middle level, G0, then there is no light coupling. So they stay there. They are forced to stay there because they cannot come out of it because there is no light to pump it out. So essentially, all the atoms get pumped to G0 state after some time. The pi-polarized light does not couple to G0, E0 because the symmetry of the levels provide a transition probability, net transition probability 0. So when I switch on a pi-polarized light, they couple only G plus to E plus and G minus to E minus, and G0, E0 is technically called as a forbidden transition. Now so all the atoms end up here and they stay there. So they get trapped in that sense. So this is one of the trap states, of course, happening out of optical pumping, not due to coherent phenomena, but nevertheless, it's a trap state. And now if we switch on these beams, they pump the atoms out. But this is the more interesting configuration. This has been traditionally called as a lambda configuration, and it's been known to create what is called as a coherent population trapping. I'm just explaining. A lot of people will know about it, but there may be some new students who are not familiar with this, because in the 90s and early 2000s, a lot of work was going on in these things. It was quite popular. And the coherent population trapping is essentially a superposition, as shown here, of this state and this state, and with a particular phase difference between them. It has to be like this. And the reason why this becomes a trap state is that when I try to look for a transition probability for this combined state to the state E0, I will get an E0 G minus E0 G plus. So the net transition probability is 0. So although the atoms are here and the lasers are on, there's no absorption on going to this state because there's no transition probability. And therefore, because of quantum interference and a coherent superposition, the atoms are trapped in this state. So now we have two trap states. One is a state where all the atoms are trapped here. The other is a state where all the atoms are trapped here. And I can switch on between these two trap states by simply switching on these two lasers. I switch on the pi-polarized light, I'll get a G0 trap state. I switch on the sigma plus sigma minus lasers, I'll get the coherent population states. So now we are going to map these two states. The traps, this state I will call it as psi 0, and this state I call it as psi 1. And in the area of quantum information, I would like to map this to bit 0 and this to bit 1. Okay. Now, what is interesting is that what happens if I switch on both the lasers simultaneously and of equal power. Okay, and not necessarily equal power. And it turns out that the system does have a dress states. Again, for those of you who are not familiar with the idea of dress state is a eigenstate of the overall Hamiltonian. These are normally called the bare states. The atomic states are the bare states, which are essentially eigenstates of the atomic Hamiltonian. When I put on the field, normally students would have started working with perturbation theory. But if the field is very strong, I can't do a perturbation theory. Rather, perturbation theory is not valid. Even if field is very weak, I can do a perturbation theory. But I can generate a new eigenstates, which are called the dress states, as opposed to bare states. So if I have all the beams like this on, I will get a multi-component dress state, and that multi-component dress state will look like this. So you can clearly see that there is a G0 here, and there is actually a G minus minus G plus here. There's a minus sign here. So essentially, this is psi 0 and this is psi 1. So I have a superposition state of these two bits. So a superposition state of 0 and 1. I'll talk more about this in the last slide of it. But I can essentially rewrite this as some parameter theta. And for sake of convention, I'm going to use theta by 2 rather than theta. And this whole state can be rewritten in this format. And exponential I phi is an extra phase factor that has been phenomenologically added over to this. It's not coming over here. And this can, if I try to break it out, theta by 2 will be simply the ratio of the Rabi frequencies of these two beams, sigma pi and sigma s. Sigma pi is the pi polarized light, sigma s is the sigma polarized light, and Rabi frequencies ratio means the ratio between the electric field amplitudes of these two lasers, or intensity, square root of intensity. And sine theta cos theta turns out to be some depending on the Rabi frequencies alone. Okay, so now the phase factor will be simply the phase factor between these two beams. These are the Rabi frequencies or electric field amplitudes. Okay, so that's what it will be, very simply calculated. And another interesting thing is I'm always having together a sigma plus and a sigma minus beam. So let me just go back a little bit to the picture, because in the next thing. So I have a sigma plus and sigma minus beam. So if you go back and look at how the electric field amplitudes are related to this will be Ex plus Ey. This will be Ex minus Ey, because I need a sigma plus in the XY plane, whereas this is in the Z plane. So this will be an Ez, be the amplitude of my electric field when I write it as E exponential ikz minus omega t. This will be only Ez, and this will be E plus Ex plus Iexy, Iey, and this will be Ex minus Iey. So the combination of this will be simply twice Ex. So therefore, essentially, this is a plane polarized light in the X plane. This is a plane polarized light in the Z plane. And the atom is going to resolve the plane polarized light in the X plane as a combination of sigma plus and sigma minus, and appropriately coupled to them. Therefore, experimentally creating this is also very, very easy for me. All I have to do is to have a polarizing beam splitter and take this as the Z polarized beam and take this as the X polarized beam. So now this atom is having one Z polarized beam and one X polarized beam. What are the intensities between these two? And therefore the Rabi frequencies between these two is controlled by this halfway plate. So by simply rotating this halfway plate, I can change the relative intensities between these two, and still maintain one very important requirement, which is that sine square theta and cos square theta should add up to 1. That means the net energy should be same, and it should be simply divided between these two, right? So I'm achieving this in a very, very simple format. And the phase factors, the phase fluctuations between these things don't really matter at all, because it's derived from the same beam. Any fluctuation in this beam will also be fluctuation in this beam, and so it's all it'll be a very robust system. Although till date we have not done this. This is a theoretical study. Okay. So we have two trap states, both in ground zero. So I'm going to map them to bits 0 and 1. And most important thing is this one, that if I take a bunch of atoms and there I can create all of them into state mf equal to 0 or bit 0 or bit 1, depending on what is my requirement, or I can do it in a combination, as we can do this one. Okay. Now here is this is something standard sigma plus sigma minus polarized beams that laser cooling people keep using, and we can show that it's easily explained in the book, laser cooling book by Metcalf, where what you end up getting by oppositely polarizing sigma plus sigma minus is I have only changed the notations here. I've changed this thing because normally people will talk about plus x and minus x, plus z and minus z. I've changed the orientation here, but what I'll end up getting is a EY and an EZ, or I can make it as an EZ and EX and EZ. So now what will happen? The polarization of the light keeps changing spatially as a cos and sine form. At some point, it will be EY. At some point, it will be EZ, and anywhere in between, it will be a combination of EY and EZ. So if I take a bunch of atoms and make this light incident on it, wherever the light is Y polarized, it will be a pair of sigma plus sigma minus combination, and the atom goes to state psi 1 or psi minus, as I have called it in some other place. And wherever the light polarized is EZ, the atom goes into state 1. So if I'm going to map it to bit 0 and bit 1, I actually have a set of 0, 1, 0, 1, 0, 1 kind of a nice lattice formation, except that provided there are no atoms in between. In between, if there are atoms, they are in a combination of 0 and 1. That I'll come back a little later in my last slide. Okay. This was just to show that we did a density matrix calculation to show that indeed the system is going to be in this format. Okay. And okay, so atom can be prepared in either of the state with a certainty. That's one thing. Atom also can be prepared in a superposition of these states. That's the most interesting part. I'll come back to this in a little later, but first we will look at what happens if I put them in 0 specifically and put them in 1. Okay. And the other part is this. I mean, this is something very important, because if I simply switch on the laser and switch off the laser, the sigma plus sigma laser and the pi laser, the atom of course absorbs the light and goes from one bit to another bit, but this is an incoherent process, and that involves there'll be some phase fluctuations and all. But using the three atomic state superposition, or what I would call as a total state, this particular total state, I can manipulate sigma pi and sigma s by simply rotating the half-wave plate in a very, very smooth fashion, adiabatically slow, that the atom always stays in one of the eigenstate of the of that eigenstate, what I'm calling in the dress state, so that I can smoothly vary from 0 to 1 and back and forth, which is a coherent transfer. So I don't have to worry about incoherent processes also. Okay. So there are about 3 uses in the next 20 minutes or so. I'm going to discuss about it. Now I know I can prepare it, so I'm going to talk of 3 different applications. One application is that there is a spin-spin interaction shift. So if I take 2 different atoms, any 2 different atoms, and prepare one of them in psi 0 and prepare another one in psi 1, which is equivalent to one atom being in bit 0 and one atom having a bit 1. I will have and bring them together. There is a spin-spin interaction, and this is the interaction is very similar to dipole-dipole interaction. So if you look at Kohan Tanuji's quantum optics book, quantum mechanics book, he is going to discuss both of them in 2 consecutive chapters, spin-spin interaction and dipole-dipole, and they give you the same mechanism, except that the signal strengths will be very, very different. Spin-spin interaction will be much weaker compared to dipole-dipole. Okay. So there are interactions. Because of this, what happens is, if suppose there is no interaction at all, then I have 2 atoms, both of them in 0, 0 state, and one atom in 1 state and the other atom in 0 state that has a high energy, and the first atom is in 0 state, the second atom in 1 energy. Both of them will have same energy state. They'll be degenerate. And that is when I don't have any interaction between them, if they are very, very far off. And if both the atoms are in state 1, I'll have a much higher energy. This energy is same as I showed you, which is proportional to Larmor precision. Omega is the Larmor precision frequency. And both of them will have the same energy. However, when I bring them closer, there is a dipole-dipole interaction or spin-spin interaction between them, which is same as dipole-dipole interaction, because of which they go to a superposition state, a dress state, which involves the spin-spin interaction, and one of them will have a higher energy than the other one. But more importantly, this becomes a forbidden state. So I cannot take the atom. This is now the combined two atom state. If from the combined two atom state, I cannot take it from here to here. It has to go via this process only. And therefore, if we are trying to do a spectra, if we take a spectra, that is, if I simply shine a light and scan its, or rather like an ESR program, if we do, I will get a splitting if one of them is in state 1, the other one is in state 0. So this is a selective transition. Okay, if both of them are in 0, 0 or both of them are in 1, 1, I'll get a transition. If one of them in 0, if I have any one of them in 0 state and 1 state, I'll end up with a forbidden transition. So this will show me that the state is in one of them. This is similar to if I kind of make an equivalent truth table, I'll have a similar to a quantum controlled phase gate or a controlled NOT gate. Okay. And the problem with that is if both the atoms are very similar, I don't have a control over which is a control bit and which is a logic bit. So there is a workaround, although this workaround makes the interaction strengths much smaller than the same atom. So I can have two alkali atoms, rubidium and sodium. And in this case, this is not degenerate. That is the first part. And more than that, there is a frequency shift for this and a frequency shift for this. So I have a specific frequency for rubidium being in 0 state and sodium being in 1 state, or vice versa. This is one of them and this is the other one. And therefore, I know I actually have a control on which is the control bit and which is the logic bit. So, and it's under my decision. I can decide that rubidium is control bit and sodium is logic bit, or I can decide vice versa. And for each of these decisions, the frequency at which I'm handling is very different. The omega 1 and omega 2 are different. So whether I'm going to use scanner on omega 2 minus omega or omega 1 minus omega, it's under my discretion. So I can do a quantum computation in a sense. I have a gate for quantum computation. Okay. Sorry, I kind of messed up a little bit. Sorry about this. I'll have to come back to this portion. That is the okay. So here I have a linear arrangement of atoms in different spin states. And if I switch on a very low external magnetic field, something that does not completely disproportionately do some Zeeman shifting and all that stuff, we'll do a Zeeman shifting, but a small amount of Zeeman shifting, then all these atoms will align depending on their state. They'll align at different thetas with respect to external magnetic field. And when I have very dilute gas, the arrangement are quite far off. In fact, I can first start an optical lattice so that atoms are trapped only here and here and here and here, so that, and then I can switch on the sigma plus sigma minus beams so that I will have exactly a spin aligned in the y plane, xy plane, a spin aligned along z, a spin aligned along xy plane, a spin aligned along z, like that. So I will have what is an equivalent of an Ising model in a solid state physics. Not exactly the Ising model, because there they are looking at spin up, spin down, spin up, spin down, but I can have a spin up and a spin 0, a spin up and a spin 0, a spin up and spin 0 kind of thing. And then we can just shut off all the lasers and allow them to interact between themselves only in the spin-spin interaction. And then we can look at what happens at the end of it and whether it will exactly mimic what the Ising model predicts, or it does not mimic what the Ising model predicts. And that will be what that's how this falls into what many people are looking at, how we can mimic a regular system using laser cooled atoms and spin-spin interactions among them. There are, I mean, this is not exactly a quantum computation, but a quantum simulation of a large scale solid state physics system. So that will be the second application which we can achieve using this scheme. Okay, we can also do where there is no optical lattice, but kind of have a bunch of atoms, each of them in a different spin system. And then in that case, there is a continuous variation of spins along this one, because if you look at this scheme again, I kind of rewrote this whole thing in a slightly different manner because it makes a little more sense. And so there is an omega, sorry for my notational mistake here. This was what I calling it as omega S. I've changed it to omega sigma here because I've merged two different presentations, and I was a little bit careless on that one. And only now I'm realizing it. And omega pi, of course, remains omega pi. And so this is my net state. I had earlier written it this way, so I'm just showing you. I can rearrange it this way. Again, the same thing follows. I have if I can vary theta continuously by varying the ratio of omega sigma and omega s, so I can have any vector on the parametric space mapped out. So this is what is of late people are looking at, called as a continuous state preparation. And I can have any continuous state. There's a small issue involved, which when we submitted a manuscript, the referee pointed out, and I know it's correct. I'm just kind of finding out words to put it. The referee pointed out that there's a little bit of a counterintuitive system that my maths is giving, because we started by telling that if I switch off the pi laser, I will get a psi 0. Sorry, if I have only the pi laser, I'll get a psi 0 state. If I have only sigma laser, I'll get a psi minus state. But this mathematics shows it the other way around. If I put this to be 0, this whole system becomes 0, and I'm not getting a psi minus. If I put sigma minus to be 0, I'm getting a psi minus. So this is a counterintuitive thing, but it's not exactly wrong. It's just that I'll have to find out the right words to tell what is this one. In any dress state, you will find that I'll have to actually do the transition and then show that if I show the transition from sigma minus, when I have only sigma minus laser, what will be the transitions? I'll get the correct endpoint. And in any kind of dress state, if you look at the standard coherent population trap state, you will always find that the dress state contains the coefficient of the component in the dress state is always the other one, right? If I, just to give you an idea of what I'm talking about, let me go back to this picture of the CPT. And okay, so let's look at this CPT. So I will have this state is incomplete because I have removed some of the coefficients here. And because if the coefficients are same, it'll get cancelled out. So I'll get 1. But if the coefficients are not same, I will have omega E0 G plus as a coefficient of this state, and omega E0 G minus as a coefficient of this state. So that when I calculate the transition probability, I'll get a mod omega square on both of them. And that's where it works out. So that is a little part I have to work it out now very clearly, because I'm writing the answers to the referee comments for the continuous state preparation. But in principle, what we can have is we can have a continuous state preparation to any one of them. and then act my quantum information Hamiltonian, and it for each continuum state, it's going to give me a different result, and which we can probe and see. And this is the other thing I told you about. I just rewrote. If I have a bunch of atoms instead of an optical lattice, if I have an optical lattice, I'll get an Ising model because I can control where the atoms can sit, and it just matches to be the lambda part of it. But on the other hand, if I simply have a continuous bunch of atoms, I'll have a continuously spin states along with this thing. And then we can look for how the spin-spin interaction leads to what a lot of theory has been worked out in what is called as a spin squeezing and stuff like that. And we can see if we do get a spin squeezing or not. That's the second part, which is just kind of yet work in the progress. And I think I've closed down a little earlier because the work is a bit short, and I'm skipping a bit of details because some of these things are worked out details in standard textbooks. The mathematical derivation is same. I'm simply applying it to a particular state. So at the end of it, what we have done is I had a conclusion slide. Yeah. So at the end of it, we have taken that any alkali atoms which exhibit two different trap states, they are, if you look at the spin of them, they are orthogonal to each other, and the atoms can be prepared in each one of them, either one of them, depending on our control. And they are also, when I start doing it, both the CPT state and the optical pumping state are endpoints of the transition. That means once the atom goes and reaches that state, it's not going to come out of it, nor will it interact with the laser anymore. So even if the laser is on, it's not going to interact with it. Therefore, we are not so critically worried about, when we are doing state preparations, we have to be very, very worried about my exact pulse parameters. Even if there's a small change in the pulse width or my omega Rabi frequencies, the endpoint will be very different. But in this case, it's immaterial to the fluctuation. If your omegas are a little lower in number, I will end up a little later in the end state. I am talking of a situation where I have only the pi beam or the sigma beam. In that case, it will take a little longer to reach end state. Or if I have an extremely strong beam, it will reach the end state, fluctuate a little and settle down. But the endpoint is always fixed. So I don't have to worry about those very precise pulse manipulation is not necessary. And in fact, I can use CW lasers. And these two states are made up of different Zeeman sublevels. So they are different spins. So in a magnetic field, they align very differently. And then we can create a very different combinations of spin states using this, and it can be a continuous state. I can take it continuously across a spin from one spin to the other spin.
Sure.
And yeah, and we can do a spin-spin interaction to do Ising, like I showed you, a quantum control NOT gate and a control phase gate. And being trap states, they are robust and they're all ground states, so they are free from decoherence effects. So that will conclude my talk. Thank you very much for listening to me, and take any questions.
Okay, thank you, Ashok, for finishing in time
Yes,
before
thank
the
you.
lunch.
Yeah.
So anyone having question can unmute and ask questions from Ashok. Otherwise, I have
hungry.
one question, Ashok,
Sure.
very
Yeah.
like general question.
Yeah.
So you have been working on laser cooling experiments, okay?
Right.
And you have set up also in your
Yes.
lab.
Yes.
So what is stopping you to do this experiment? Like how far you are there from this experiments, like making this atomic qubits, spin qubits?
Not very far, not very far. The laser cooling system, a stable system, we got only running a couple of months back.
Mhm.
And so I'll have to, and we are going to kind of shift from a old building to a new building, so the lab will be shifted, but then
Mhm.
I'll have a much better configuration where I can have a optical lattice kind of thing. So since I have not done the optical lattice experiment, I have to go a little bit of step by step. We are not very far, probably maybe a year or so I'll be able to
So,
do.
why you are preferring optical lattice instead of optical tweezing? Because this you look in group. However, they are
Okay,
using optical tweezing. You are expert
tweezing,
in
yeah,
tweezing. So why don't you use, like, you will have
we
better
can
control if you go for
we
tweezing
can do that. We
of
can have an
that.
optical trap, and yeah, so that I'll look into that part. Optical lattice, I was only looking at having a nice arrangement of
Because you
atoms,
can
each
apply
of them
your
in different
expertise
strength.
of optical tweezing. You can follow Lucas
Yeah,
paper. They have done, like, using
yes,
optical tweezers.
sure.
So,
Yes,
okay.
I have come across
And
this paper. I've not looked seriously into
so
it, but yeah, I'll look
what
into this.
I was trying to follow, generally this
Hmm.
atomic system, when they talk of this atom trap and all, they
Hmm.
talk of like optimization problems, doing optimization problem, but you are talking of like qubits and operation and qubits and all. So you are talking of universal quantum computing instead of this optimization thing, something like analog quantum computing.
Something like analog quantum, not necessarily. Yeah,
But
we
you're
can
talking
do
of
an analog quantum.
you are doing operation on qubits, two qubits, and single qubit. So are you going
Yes,
towards like universal quantum computing instead of like
like a
this
universal. Yes,
optimization and annealing and all? Okay, that's good.
more like
Something
that.
different.
Something
Very
different.
nice.
Yeah, yeah.
So any other
Optimization
question?
also will
Mm,
become when I have a bunch with a lot of systems. When I look at its dynamics, I'll be looking at
mm,
optimization problem
mm.
only. So I can do either of them. I have a
You can do
either of
either
them.
of them once you have
Yeah,
good calculator.
right.
That's really interesting. Anyone else having question?
People must be hungry.
There are 70 guys logged in, but
Yeah,
nobody is having question. That's really surprising. Uh,
maybe they understood everything I said. I'll take it. I'll take it in a plus point. Yeah,
okay, chalo. Then thank you, Ashok.
right.
It was nice
You're welcome.
listening to you. Yeah, it's nice. Very,
Right.
very nice talk.
Thank you
Interesting
very
one.
much.
Sure,
Thank you very
thanks. Yeah.
much.
Let's conclude this session then. Thank you. Bye.
Thank you. Bye.
Hello, Prashantji. Any announcement?